Hello. Previously we looked at converting quadratic expressions from standard form, as we see here, to vertex form, using the process known as completing the square. So the issue is, when we looked at all of the examples had the a value, that is the coefficient on x squared, was 1. What if the coefficient on x squared is not 1? It poses a slight problem, especially because 2 and 3 and most other coefficients on x squared are not going to be perfect squares. So just as before, we got rid of the negative 3, we're going to have to devise a way to get rid of this 2 so that we can still construct a perfect square and maintain equality. So what we're going to do is we're going to start by kicking out the 3 like always and just focusing in on the first two terms of the quadratic expression. And then, regardless of the b value, we are going to divide out whatever a is from both of these terms. In other words, we're going to factor out a 2 in this case. So I get this. Now you'll notice I left a space for a number to choose. This is going to be the number to make a perfect square, but what we need to do is focus on this trinomial, now it's a binomial, inside the parentheses. This is the thing we're going to make a perfect square. The 2 and the negative 3 are there to maintain equality with the original expression. So just as before, I'm going to create my Xbox with my new b value and find numbers that add up to give me 4 that are the same number. In other words, take half of 4, you get 2 and 2, which means the c value, the magic number, has to be 4. So I'll put the 4 right there. Here's where we get into equality. When adding a 4 inside the parentheses of this expression, I haven't actually increased the value by 4. I've increased the value by 4 times 2. So this 2 is still affecting the values of the outcomes for this expression. And so the effect of adding 4 inside is actually adding an 8 outside. Now, in order to maintain our balance, we have to take this 8 that we've added to the expression and subtract an 8 so that the balance is restored. So here I add 4, which is effectively 8, and that's what I subtract on the outside. The rest is factor the perfect square and subtract the two numbers here. We're good to go. So in the second example, what makes this one interesting is factoring a 3 out of the first two terms is challenging because 5 is not a multiple of 3. That doesn't change the fact that all we have to do is divide both expressions by 3, or both terms by 3, and then leave the 3 out front. We can see if we distribute the 3, we would get 3x squared plus 5x, which is where we started. So now, with the 5/3 as our target, we create our Xbox. Half of 5/3, as we learned, you just double the denominator, is 5/6. And that leaves 25 over 36 as the magic number to make a perfect square out of the expression shown. So I add 25 over 36. But now I have to actually calculate the net value of 25 over 36 when it's multiplied by 3, and that's what's being added to this expression. Usually people will multiply numerators. 3 times 25 is 75 over 36. If I could reduce, I should, and it'll always work out this way. You could divide the 3 into the denominator and effectively show that I've added 25/12. 3 goes into 36 12 times, so we have a 12 denominator, 3 times as big as that. So 25/12 is added, I take that away, and the rest is rudimentary. We factor the perfect square and collect the like terms, and that generates this final result. Just as a reminder, what we're doing here is taking a standard form expression and writing it into vertex form. A, so that we can read the axis of symmetry, the vertex, right off of it, and B, because now I could take this form and use inverses to find x-intercepts and solve the equation. Two more examples for a values. We looked at positive whole number a values, but what happens if a value is a fraction, and what happens if a is a negative number? We'll deal with both of those. For fractions, remember, dividing by a half, in this case, is equivalent to multiplying by 2. So when I remove the 1/2 from the first two terms, I'm actually going to get not x squared plus 2.5x. It's actually going to be 10x. Notice if you redistribute, 1/2 times 10x equals 5x. So this is the correct b value. Create the Xbox, and 25 becomes the magic number. The net value that I actually added to the expression is 25 halves. So basically take half of 25. The rest is factor the trinomial and collect like terms. Now we're in vertex form. Finally, in the last example, this time the a value is just -1. That still has to be removed from both terms. So here, when I take out the negative, I get x squared, which is now positive, and then I should have the opposite of 8x, which is minus 8x. Now at the x box using -8, I find 16 is the magic number. And here's the most common mistake that students make in completing the square, forgetting that the 16 is not being added in value. We're actually adding a -1 times 16. So we're really reducing this value of this expression by 16. So that's the net value. I have to counteract this, which means instead of subtracting 16, I'm going to add 16. So this part right here, again, most students who don't know what they're doing will make this minus because they just figure every time we subtract, which is not true in this specific case. Notice add 16, add 16. It kind of looks weird, like it's imbalanced, but it's that negative is changing the balance. Excuse me. And finishing this up, we have this vertex form equation. Now, we talk a lot about analyzing quadratic expressions and functions. If this were a function, this is just an expression, but if it were a function and I was to look at its graph, I could make that quick mental sketch and see that we expect a parabola that opens down. And the vertex, a quick calculation for axis of symmetry, -b over 2a, the vertex is going to happen when x equals 4. And because the parabola opens down, we should anticipate the vertex to be above -3. So it should be up top here somewhere. Now, the reason for this mental sketch is to anticipate what we should expect when we do all of our algebra here. So what I'm going to do is I'm going to demonstrate the completing the square process, factoring out the -1, and this time though I'm going to make that mistake that is so common. Students see plus 16, so they take away 16 here to keep it balanced, and then let's look at what happens. We end up with a factored expression like this. That means that my vertex has to be at 4, -19. And 4, -19 is way down here. And there's no way that we can make a parabola that opens down and has a y-intercept of -3, and yet whose vertex is down here at -19. So it's really important that we make the mental sketch so that we can catch very subtle and very simple mistakes like the one I made here. So don't forget, before you just dive right into completing the square, spend a few seconds just thinking about what kind of results are you going to expect when you do complete the square.